And also, this was a, you can always go back and view the recorded session here. We will probably post it already tomorrow. So come back to the 10 in Motion website for the webinars, and you will be able to see it again. Now I'm going to hand over the presentation here to JB, and going to make him a presenter there.
Yeah, seems to be it.
Okay, good. Perfect.
Excellent.
All right, JB, you take it from here. Thank you so much for being here. Thank you.
Thank you very much. Thank you, Peter, and thank you guys at 1080 for inviting me. So yeah, it's a great pleasure to be here and present today. So I'm going to present today and to focus on the methods. So we're going to talk about how and what you can assess in sprinting people if you want to use that in training, rehab, or whatever scenario. So it's going to be about the methods, the advantages, and the limitations. So if you want to go further and see some more content, access to our publications, all that stuff, I suggest that you go to my website. Everything is open access and free there. It's jbmorin.net. And there's also a contact form if you want to contact me further. So whoops. So that's the beginner mistake on my end. So that's one. Basically here, what is wrong? Was it on the last slide? Yes, it was. First time in my life that I begin a show with the last slide.
No worries. I'm glad I'm not alone making mistakes. You're good.
Yeah. That was my starting joke. I just want to declare it's not a conflict of interest. It's something people need to know. I'm a scientific consultant for 1080 Motion. It doesn't affect my judgment, scientific activities, but I'm going to talk about the 1080 during this presentation, so everything is clear. So the research as we see it is mostly a research where you start with the macroscopic approach of your performance. So typically jump weight, sprint time, and you try to then focus not on every single piece of the puzzle, but first on the big picture of the puzzle. And it's something that we learned from mentors. One of them was my PhD supervisor, Professor Di Prampero. And the other is Robert McNeil Alexander, and he published this paper, Modeling Approaches in Biomechanics, where he says, the simpler the method, the simpler the model, sorry, the clearer it is what feature is essential to the calculated effect. And in sports, the calculated effect is performance. So this approach doesn't mean that we don't care about the underlying mechanisms. It just means we focus first on the main outputs, what force output, what velocity output, before going deeper into the specific mechanisms involved. So another philosophical introductory here is I want to talk about two main rules in our work. It's the rule of parsimony and simplicity. And this has been discussed in sports science by this editorial by Aaron Coates a few years ago, where he says, citing the Occam razors principle, and he says, entities should not be multiplied if it's not necessary. And the simplest solution, let's say the simplest model, the simplest valid model is most likely the right one. I would say maybe it's not the right one, but it's the one that allows you to go further into your analysis. You can always complexify things. You can always go one step more complex in everything, because there's nothing more complex than the human body performing. Okay. Big question is, what is the balance between how complex / simple is your approach and what you can do with it? Okay. So remember this quote by Da Vinci: simplicity is the ultimate sophistication. You have to take things down to the simplest level of analysis that is still valid, reliable, and actionable. This is very important. And so last quote for this introduction, Einstein, I love this one. Everything should be made as simple as possible, but not simpler. It means you have to stop where the modeling doesn't fit reality anymore, or where the modeling is starting to have a magnitude of error that's not acceptable. Okay. So that's the deal today in sports. you're crawling under tons of data, okay? So every training session, you can spit thousands and thousands of data, but this question, that's the key question in my opinion, training should be individualized, should be answered with another question. Okay, fine, but based on what? What are the metrics I'm going to use to individualize training? What will I have to measure and what will be useful or not? Because I can basically measure everything, okay? I can measure things on an athlete. The big question is, what will I use to orient training effectively? So let's keep calm and go back to some basics. So I'm going to have some biomechanical basics here. For very long, the model of sprint performance has been running is the product of step length by step frequency. For example, if you go with a step length that's 2.5 meters and you do 4 steps per second, your velocity is 10 meters per second. This model is correct, mathematically speaking, but the big issue is that this model is, let's say, historical, just because at the beginning we could only measure step length and step frequency. And so this model says, well, if you want to be a better sprinter, improve step length, improve step frequency, or improve both, and you will sprint faster. But the big issue I have with this model is that it's correct, but it is not a causal model. And if I advise that you really go on YouTube and listen to that presentation by Aki Salo, a researcher from Finland, where he exactly discussed how this model was built in the history of biomechanics and how this model is the good example of something that's correct, but not really actionable, okay? So I tend to prefer another view of things, and I tend to prefer Newtonian dynamics, because Newtonian dynamics, the laws of motion, tell you the causes of our movement. If I sprint fast, it's because forces, my forces, the ground reaction forces, friction forces, etc., gravity, my forces have induced the movement of my center of mass, and that's the cause. That's the number one cause of my movement. Step length is not the cause of my movement. Step frequency is not the cause of my movement. What made my body move was forces. And so this sentence by Einstein says, it's not because you can measure something, step length, step frequency, that it counts. Not everything that can be counted counts. And that was a good example with step length and step frequency. So let's go on to some more dynamic approach of sprinting. So this is how we see things. So this picture is from a book that's about to be released, High Performance Training for Sports at Human Kinetics. So in this book, I wrote the speed chapter with Stuart McMillan from Altis. And basically, the model is very simple. At the center of the model, it is the essentials. What are the essentials to move? Produce force with your muscles, okay? And transmit that force to the ground with effectiveness. We'll see what effectiveness means later, but if you want to accelerate, basically effectiveness means forward orientation of the ground reaction force and very fast action so that you can pound the ground with high force and short contact time, basically. Then you have some specifics to the sport, and here I wrote the team sport specifics. And for example, fatigue, variable positions, you need to be able to do, produce, and transmit in these conditions. And on the other side of the model, there is the context. And the context of sprinting is movement velocity. Sprinting is a very fast action. So you need to be strong, but you also need to be strong in a very fast action context. And this is totally different from being strong in absolute terms. Many athletes who are able to push thousands of Newton on the ground during a leg press or during a squat are not able to push these thousands of Newtons when the contact time is as short as 100 milliseconds in sprinting. So movement velocity and very short contact times are key pieces of the model. If you forget that, then you might miss the point. And then this is the spectrum that you see at the bottom of the model. You need to be able to do all of that from acceleration to maximum speed. And this is not either acceleration or top speed, because both are totally linked within an entire spectrum. So depending on the length, duration of the sprint, it's going to be more acceleration oriented. If the sprint is faster, longer, like for example, at the 100 meter, it's going to be max speed, but it's clearly a spectrum. So you need to be good at force production, good at force transmission over a complete spectrum. Now, how can you do that? Well, you have to be able to measure two things. First, the kinetics, the dynamics, the forces that drive your center of mass in the direction of motion. And basically in sprinting, the direction of motion is very often right in front of you, okay? So that's measuring ground reaction force. That's the force that drives your body with gravity, of course. And you need to measure and quantify the kinematics, and kinematics are the segments, movement around the center of mass. So basically you need to be able to assess how the center of mass moves and how the segments move around that center of mass, because the segment's position basically define the center of mass position. So that's the main framework around which we work. And here you have two circles here. One is around the hip extensors and one is around the calf and ankle, because some recent studies showed, and previous studies as well showed, that hip extensors, the posterior chain machinery, and the quality of the transmission at the foot and ankle are key components of that entire model. So just for example here, in 2011, we suggested that the orientation of the force, of the ground reaction force vector, was key to acceleration performance. And this has been confirmed with many different research teams since then. Clearly, if you want to accelerate forward, it seems to make, it's an absolutely no-brainer. You need to be able to orient the ground reaction force so that the center of mass of your body is pushed forward. And basically, Newton said that already. He said, so this is, if Newton had Twitter back in the days, 17th century, he would have tweeted his law of motion in 2 tweets, not only one, because it was too short, but everybody would have missed the second tweet. So this is the first tweet. The tweet of Newton says, the change in motion, which is acceleration, is proportional to the motive force impressed. Impressed means impressed onto the ground. And if you just read that tweet, you say, bam, if you want to accelerate, whatever direction, then you need to put some force onto the ground. But there was the second tweet, and everybody missed the second tweet. The second tweet says, the direction of the acceleration will correspond to the right line at which the force is impressed, which means more force means more acceleration, but in the direction of the force application. So it means if you want to accelerate forward and you push the ground without a good forward orientation, then you're going to accelerate, but not in the horizontal direction. So the component of the force will be not very efficient. So to summarize that, that's the picture I love, and I stole that to my friend Jordan Mendiguccia in one of his presentations. If you want to be a Formula One, you need a motor, you need to produce force, that's the basically muscle machinery, and you need every other component into the system that will apply, transmit that force. And you understand that if the motor is big, if the motor is powerful, but if every piece of the transmission chain and every connection between the pieces of the transmission chain are weak, then your Formula One will not be good. Okay, so figure out a Formula One on flat tires. That's not going to be a powerful vehicle. Okay, so now that the concepts and the framework have been defined, let's go to the methods. How can you do that? So we wrote, well, Matt Cross, the students I'm supervising, wrote a review of literature a few years ago saying, okay, if you want to profile the power, force, velocity output in sprinting, how can you do that? And woo, the conclusion is these athletes are moving 10 meters per second. Even in slow motion, it's fast, okay? So how can you measure ground reaction force, kinematics, blah, 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 in something that moves at 10 meters per second or more? So basically here today, as I speak, you have two possibilities. I call that impossibilities, because you can either find a lab where you have force plates into the ground, like in the INSEP in Paris, they have 7 meters force plate system, or in Japan, the wonderful lab of Ryu Nagahara, they have a 50-meter force plate system. Boom, 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 boom. 50-meter force plate. You have everything. Great. Or you can go to Saint-Étienne in France. That's my former lab, and hopefully my next lab, and to Doha in Qatar, because in these places you will find a treadmill that works like that. It's a treadmill on which you can accelerate from 0 to very high speed, not exactly your typical field high speed, but very high speed. And the treadmill responds to your pushing actions and wonderfully measures the 3D reaction forces. So with these two devices, you can get the kinetics. Happy? No, not happy, because you will never have access to that. So now, as a researcher, I could say, thank you guys for listening. End of the webinar. Bye-bye. But we try to provide some methods to quantify these kinetics with field devices. So how can we do that? Basically, this is something we've published first in 2016 with Pierre Samosino. And everything is based on the fact that when a human being accelerates from 0 to maximum speed, whoever they are, I think I have no measurements where it's not the case, except some professional football players trying to cheat the test, okay? But if you go all out from 0 to top speed, your speed will accelerate, okay? But it will accelerate following a very simple mathematical equation that you see here, that is based basically on two variables, the top speed and the time constant of acceleration. So it means that Christophe Lemaitre, the French sprinter, European champion, etc., increase velocity from 0 to top speed with this model, fitting very well. Football players, rugby players, ice hockey players, if you've listened to the New Jersey Devils people webinar, you've seen that, I guess. Usain Bolt, during the world record, the acceleration was exponential. So the fitting of the raw speed data was perfect with this model. My son, 4 years ago, I asked him to accelerate and he followed that exponential trend. Very old athletes here. You have a 96-year-old athlete that we were able to measure at a masters competition. He's going from 0 to 16 kilometers per hour, but his acceleration is following that exponential decay, okay? So from that constant and consistent observation, we said Newton dynamics allow us to calculate in the direction of motion from the position and speed, the acceleration, and from the acceleration over time, we can estimate the ground reaction force that was basically driving the center of mass and the link between acceleration and force is with body mass. So you can go into the details reading the paper. I will just say that we estimate the air friction and we used basic laws of motion. But we were absolutely not the first to do that. And this is something I have some time to remind to some, let's say, acid people, like reviewers or people on the net. We did not invent that model. Basically, observations by Archibald Hill, the Nobel Prize in exercise in physiology, as early as 1927, with this kind of machine, measuring the speed trace of a sprinter, as you can see here, we have in these papers exponential acceleration that was already observed. So it's a very commonly observed behavior. In this picture here, so that's 1927, it's almost 1 century ago. So Archibald Hill is basically the professor here with a wonderful white shirt and tie and shorts. That's amazing style. as early as 1927, the first observations say when someone accelerates, wow, the mathematical function that fits perfectly what's happening is a very simple exponential equation. And then every researcher trying to observe that found the same. Here you have a 1979 study by Volkov and Lapin. And with this wire, let's say it's a velocimeter, so you attach the wire and the sprinter sprints, you have the velocity as a function of time that's measured here. Every tick, this is wonderful, every tick on the paper here is a 0.2 rate, and every tick here is 1 meter covered. And what do you see here? This graph says, wow, until the acceleration, there's a wonderful exponential increase in speed. So we all agree on that, and we just estimated the newtons of ground reaction force in the horizontal direction from that speed data. So the best validation of that method, so we did two validations. One was in 16 and the other one was last year. Why two? Because in 19, we were able to collaborate with Ryu Nagahara and to have some people sprint on this wonderful, it's the only lab in the world like that, 50-meter force plate system. It's millions of dollars investment, but we have now what you see on the screen here, the comparison between the increase in velocity by a laser system versus the increase in velocity by the force plate system, which is the reference, versus all the ground reaction force data within a single sprint. So what we could do in that paper, and you can go and read that paper, is the comparison between our model estimates of force and the force plate estimates of force. So this is a typical example. The points here are vertical force, horizontal force, and the equivalent power in the horizontal direction for every step. And the fine line here is the equation from our model. In summary, that study says with simple inputs, body mass, running velocity, or running time, you have a pretty high reliability, and in practice, it only takes one acceleration up to Vmax. So we will see the limitations after, but basically that's the model. So you can go simpler than this simple model because in that iPhone app, so today's iPhones and iPads are 240 frames per second, which is a level of accuracy that was gold standard video analysis in biomechanics lab less than 10 years ago. Okay, so it means for human motion, an iPhone and an iPad is a very good camera. So if you say, I use the 240 frames camera, people say, wow, that's biomechanics, baby. If you say, I did that with an iPhone, people laugh and say, come on, it's a joke. No, 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 it's exactly the same. It's a high frame rate camera. So that's what Etienne Jules Marais, the French physiologist, did more than 1 century ago. Basically, this application is based on a slow motion filming of the sprint. You mark the 5-meter splits and you calculate, the app calculates everything. So we have published a spreadsheet that's free, open access. You can access that on my website, where you enter the split times, you enter the distances, the body mass, and basically you can calculate all the model outputs. Another example is with the 1080 sprint data. So if you have a 1080 sprint machine, you can have the raw data fitted with that exponential function, and then you can calculate all the force and velocity outputs of the model. And basically you can have the maximum horizontal force output, the maximum power, and the profile orientation. And you can calculate that orientation of the force that we call mechanical effectiveness. But think of that as the orientation of the ground reaction force vector. And same here, we have published in the very same spreadsheet, there's another sheet where instead of having the split input, you have the velocity trace input. So you export the velocity trace of your 1080 machine, you type and you paste the velocity data, and you can run exactly the same analysis, okay? So just an example here, very quickly, we had fun around the Usain Bolt's race, and just knowing the speed data of Usain Bolt during the world record, we could calculate everything and all the outputs just to describe the force capacities of this wonderful athlete. Now I'm going to talk about another type of relationship. That's the load velocity profile. It's not the force output velocity, it's load velocity, because it's very interesting to design resisted sprint training programs. So very simply, to build the load velocity, it's exactly like in the gym when you use the gym aware system or you use the 1080 quantum system to do a load velocity profile. You do several sprints, 4 is enough, with different levels of resistance, and every time you quantify the maximum velocity, like the average over 5 meters or the fastest 5 meter split. Then you plot that against the load. So here you have a plot of load in kilogram with the 1080, but you could do the same with a sled load versus the maximum velocity. And then you know everything because the equation of that line, that beautiful linear line, tells you the individual load velocity. And this is very important because the same kilogram on the sled or the same kilogram on the machine doesn't impact the athletes the same, because for the same mass, some people will run faster than others. So it means that you will stimulate different parts of their force velocity spectrum. They will be in a different condition. It's a no-brainer at the gym. You will never put the same load for 2 individuals to work the same velocity of movement, right? Well, do the same in sprinting, okay? So again, you have a free spreadsheet that we have generated. And remember that this is very, very, very important. If you want to test or to program resisted sprints, don't use % of body mass. Use % of velocity decrease. Because the same % of body mass on different surfaces, on different sleds, will induce very different things. If you think in terms of velocity, then you have the right way to design training and testing, okay? Exactly the same as velocity-based training at the gym, all right? If you want to have the same level of output, you need to have the same velocity, not the same load. I think this is a very important message. So now for the kinematics, what can you do? Well, again, go to some labs. You can have wonderful 3D video cameras here, like we did recently at the University of Bath in UK. We did a study where we measured the pelvic tilt at full speed, and we used something like 15 or 20 video cameras. In another project here by Ryu Nagahara, you have a wonderful analysis of sprint kinematics using 60 video cameras. Okay, fine, go to the lab. Well, it's impossible again. So what you can do in field conditions is to go back to some very simple sagittal plane 2D analysis, again, with a very high-speed video camera that's in your iPhone or iPad. And you can use the online software named Kinovea, that's free. So basically, you film something at slow motion, you do the markers and calibration correctly, then you export the video into Kinovea, and you can do some wonderful work. That's something that my PhD student, Johan Latti, is currently doing. And for example, here, we quantified the change, the acute and the chronic changes in sprint kinematics. So sprint pattern when you pull very heavy sleds. So here you have the stick figure of some sprinters when they pull 60% velocity decrease or 50% velocity decrease. And you see that when you pull heavy, your body tends to lean forward, etc., etc. And after some training like that, we quantified the training-induced changes in normal sprinting. And what do you see here? And I think this is big information for everybody. The paper is about to be published. There is absolutely no change in the sprint kinematics after heavy sled training when it's well done. It means that they improve performance without changing their free sprinting, early acceleration, or top speed kinematics. And this is very important information. And everything was done only with iPhones. Well, sorry, only with 240 frames per second cameras. I advise you that you use the Altis kinogram method as a reference because this is something that we have designed with people at Altis, elite coaches, to say we have 4 or 5 key moments into the step cycle, and this is what you're going to screenshot and then analyze in terms of angles with your software. So of course, again, this is not laboratory science, but in my opinion, it's very good level of quality and information science. So what kind of applications in testing and training? I will be very short on that because you can find some information online. What you need to remember is that many people think that the stronger you are in terms of maximum force output, the faster you will be. And many people think that the force velocity profile at different level is organized like this, but this is not the reality. The reality is when you assess a team, like a hockey team, a rugby team, whatever, and we did that with 500 athletes from leisure to Olympians in that study, that's the reality. So this is the jump force velocity profile, but we have exactly the same in sprinting. The reality says there's no connection in trained people between their level of maximum force output or maximum acceleration and their level of maximum velocity at the end of the sprint. You have some very different scenarios. So it means that strong at low velocity doesn't mean strong at high velocity. And it also means that in terms of training, you have to be sure that you want to target some specific things to improve. Well, if your athlete is good at everything, that fine, you're lucky and should have a contract with them. But it's not often the case. And so you have athletes around who were very fast, but not very good in terms of maximum force output. So they were strong in a maximum velocity context. And if you design the sprint profile of your athletes, you can think further like that. In my experience, I don't know any staff, any coach telling me, well, we've tried and we left that because it's useless. Everybody connected to that and still get some information on that. So just a quick example. I will be fast on this one, but on this one. These two athletes are from the same rugby team. They have the same 30-meter time. So it means if you just assess their 30-meter time performance, you say, okay, they have the same sprint capability. It's the same time. Thank you. Bye-bye. Let's train them the same. But if you go into their profile, you see that they are very different in terms of force velocity distribution. And also on the right, in terms of force application. So you can think about how to design some training that might be a little more adapted to some athletes. I always tell that analogy, if you and your wife or you and your partner go to the doctor and you have different symptoms and you go back home with the same medic, with the same drug, I think there's an issue, okay? It might not be adapted to everybody. So I cannot go into details because that's studies. We are now exploring the entire very heavy, very slow, very strong side of the curve to very fast side of the curve spectrum. So that's many studies ongoing, hypotheses, contradictions. That's science basically. So maybe we can have some step back and think in a few years when literature will be a bit more comprehensive. So to summarize that part before the limitations, I will talk about the toothpaste tube theory. Basically, low-level people, starters, beginners, whatever you do, you press, boom, you have results. So you will increase the performance by doing basically anything. So it's you can be a good coach with beginners, okay, systematically, whatever you do. But if you go with higher level people with less margin of improvement, then the same solutions don't work anymore. And so you have to think where and how can I push to find some more toothpaste. And we all know how to do that, okay, at home. So the idea is exactly that. Don't do the same better again and again and again. Try to adapt and do something else. Try to go where the system that you're studying, that you're training, has some margin of improvement. My experience with elite people is that you can still get some improvements even after years of training, just by changing the lens, changing the focus, and trying to find some other toothpaste in the system, let's say. So nothing comes without limitations. That's the last part of my talk today. And I love that sentence that says, anytime you model something, you're wrong. All models are wrong. You can never be as accurate as the natural biological complexity of the human run, but some models are useful. So you want to have simplifications that are actionable. So it's always the same. What is the balance between accuracy of the model? It's never 100%, and feasibility and usefulness. All right. So first source of variability and first source of error, the model itself and the method itself. In this paper by Italian colleagues this year or last year, they quantified with 35 video cameras. Okay, so that's a lab experiment. You will never get 35 video cameras, but what they say is very, very, of course, true, and I agree. And they said, with a simple method, you miss what we call the internal power. That's the power related to the internal energy exchange between the limbs, okay? And you also miss the intra-step power production because you smooth and you fit the acceleration, where in fact we know that accelerating is stop and go, stop and go, stop and go. So we agree with that. And for example, here you see that the raw velocity here is up and down, up and down, up and down, but my exponential fitting says you're basically rolling through your sprints. So yes, we miss that intra-step information. But again, if you want to have it, you need 35 video cameras and the data processing that comes with it. So here, what do you see? Well, in fact, the internal power is the lower curve here, the external power is here, and so the total power is much, much higher than what you would measure with the model that we use. Then here you have, let's say, the power with the simple method that we use, that's horizontal power only, compared to the total power and the total power plus the power in the velocity in the vertical direction. And so, yes, we are underestimating the real power output, but the big question is what we are missing really important to performance? So again, like Einstein said, we cannot count that in our model, but is it really essential to performance? I don't know. We need to measure that. Does internal power make a difference between elite athletes and non-elite athletes? I'm not sure. I don't know. But for sure, horizontal power does. And so I made this little video yesterday. In this exercise, it's a bit shaky, but you understand the point. In this exercise, I do very intense limb movements. So I have a very, very high internal power output. I also push the ground vertically a lot and my center of mass moves vertically. So I have a vertical oriented power production that's very high. And what's happening? I'm moving backwards. You understand that? So my internal power and my vertical source of power are really high, and my movement is negative in the direction of motion. So my point is, what's really important to assess is the power in the horizontal direction. I am not sure, maybe the time will tell, but I'm not sure it's key to have that. And anyway, you cannot because you need 35 video cameras in the field. Second problem, and this is very important, the initial speed data. Every time you measure speed with a radar, with the 1080 machine, or with split times, what happens at the very beginning of the sprint needs to be very, very accurate. Because if you do a little mistake at the beginning of the sprint, it will have major consequences on the force and power outputs. So for example, here, when the data of the radar are shaky and there's noise, we cut that part and we fit the entire curve and we add what we call a time constant to the model that allows the velocity to start at the real theoretical zero. So we have a smooth increase in speed. So you need a clear start. You need no pre-go movement. You don't want your athletes to, to move around and jump and then sprint because it's going to be difficult to assess the real start of the motion. You need a single all-out push, no false start, no double leg stand start, etc., etc. And you need, that's the main word, familiarization. Don't do a test, don't try to analyze data if your athletes are not technically doing a clear start, and this will need maybe for in football, for example, soccer, you need familiarization. So that's not about the method, that's about the device, that's about the subjects, and that's about data analysis. And the last problem is familiarization. This sentence is very important. Before any testing, any training, and a fortiori any research protocol, whatever the level, you need to get the athletes familiar with what you do. And this is not with the model or the method. It's not an issue of the model reliability. It's an issue with your protocol and your subjects and the analysis. So my recommendations are, if you do resisted sprints and you want to measure anything, you need at least 8 weeks of adaptations with 2 sessions per week and increasing loads. You need to progressively increase the load, progressively increase the distance per sprint until Vmax, and increase the number of loaded sprints. And it's the same with assisted sprints. So whatever you do with loads, you need to get the people familiar. So in this video, I saw one day in a research protocol that was tweeted, you see that the start of the sprint in this player is totally shaky. And basically, it tells me that this guy was not familiarized. It's maybe the first time he's pulling so heavy. And so if you think about testing here or research protocol here, then you understand that the issue is not in the model. The issue is in the protocol because there's no familiarization. So with every elite structures I work with, and every time we do research, there's a non-negotiable familiarization period. Okay, and this is not negotiable. It's the quality of the data that's at stake. So my last slide, summary. Acceleration, individual profile, and load profile bring novel informations. Okay, they are possible with field devices, and I need to focus on the feasibility, validity. Of course, it's not perfectly valid, but it's very, very, very feasible. And so you need to deal with that ratio. What do you want? Do nothing because you will never access to a 3D camera in a lab, or do something with being totally conscious about the limitations. So the limitations are non-negotiables, familiarization, good start, and good quality of measurements. And keep in mind the assumptions of the model. Keep in mind that yes, we do an underestimation of the real total sources of power, but keep also in mind that maybe what we don't measure is not very, very important to performance, okay? So that's going to be the topic of future research. So we just put our hands on something. Thank you for listening, and now it's time for questions and answers.
Thank you very much, JB, for a really interesting presentation. There's Adam, Rolf, and Ola Erksrud joining us here, who will now lead the Q&A session. So go ahead, guys.
Thank you, JB. We did have a few questions come through, and I just want to kick it off here. We had a question from sprinting with Franz Bosch and his drills. Do you have any opinion of those and how they relate to your talk?
Well, Franz Bosch has a lot of drills, and most of them, I've seen his conferences and read his books and all that stuff, and most of them are really consistent with the model I've shown, produce force and transmit it to the ground, because I think that most of them are directed to better produce the force and better transmit it and better limit what I call the energy leaks. Every time you push the ground to change direction, accelerate, whatever, there's some energy you produce and there's some energy leaks throughout your system, throughout the spine, throughout the trunk, throughout the pelvis position. So I think that overall, most of the drills I've seen in Franz Bosch, especially those trunk, pelvis, and posterior chain oriented, are effective in transferring to sprinting. There's no way we can very easily measure that, but it makes so much sense mechanically that it's to me it's totally valid.
All right, JB, thank you for a great presentation. Working in the field, you come across arguments that you cannot or should not use heavy resistance, as this will alter your movement patterns of sprinting too much. What are your thoughts on this one?
So I would say yes and no, because some cultures, some countries, some coaches are totally against, and some cultures, some countries, some coaches are totally using it, and they know, if you listen to, for example, Cameron Josie or many others, they know it's useful when it's well used, and etc. So the field is not totally in agreement, but my point is most of the against arguments don't hold to me, because these arguments are they're gonna get injured, and my argument is, are you squatting 200 kilos sometimes at the gym? Yes. And injury is not an issue for you. Okay, so the argument of injury is to me wrong, and there's no study showing that there's a risk. If it's well done and progressively done, there's no reason to get injured doing heavy resistance training compared to squatting, which everyone does, okay, or almost. Second argument, it will slow it slows the players down. Yes, of course, that's the objective. It slows them down to develop their strength, because if you don't slow them down, there's no way you stimulate that strength. And the last argument was that kinematics argument, and basically it had never been tested ever in the literature. The only 2 studies or 3 studies to date testing the kinematics of how do you run after a block of training with resistances were with low resistances, and the changes were very small. So we did that big study. Of course, when you pull the resistance, you don't have the same kinematics. It's I mean, yes, you run slow and you don't run the same, but that's obvious. The question is, when you stop training like that, is your pattern changed? And so the first answers here, soon published, say basically no. But there were soccer players totally used to do that. It was not new for them, and totally okay with the protocol, and so it was, in my opinion, well done. If you take a group of beginners, they have never done resisted sleds, you bang them with heavy sleds, and then after a few weeks you measure how they sprint, I can understand you will find differences in the pattern. I can understand that, but this is not serious in my opinion.
Here's another question from Miguel. Is it possible to use the MySprint with endurance athletes to get useful information for endurance performance?
So you can use that with anybody. So yes, you can use that. You can do that test with endurance athletes if they are okay with sprinting and all that stuff. Now the question, is it useful? My answer would be yes, because if you check the middle distance and even the endurance literature, you see that strength and high speed capability is a factor that was totally omitted 10, 20, 30 years ago. And it's a factor that's key today. And we know that what we call the anaerobic reserve, the difference between your aerobic speed and your maximum speed, is a key component of performance, for example, on the 800. And so, yes, measuring that and improving that component, in my opinion, is interesting. Not only for the performance side of things and the final sprint or whatever, but also for the muscle stimulus it brings. I am connected with middle distance coaches in France, and for example, hamstring issues are also there in marathoners sometimes, and in long distance people sometimes. So high speed running is a good stimulus. So I think endurance athletes should also add that to their training tool. Of course, it's not the #1 key factor in the performance. I understand that, but it might be a difference when everything is, you know, when you pushed every button, this might be the last button you need to think about. If your maximum aerobic speed is low, then I won't focus on sprinting too much. You get that? So
yeah.
One question in terms of team sports, because now we're talking about longer linear sprints. So if you're thinking team sports, just short accelerations. How do you apply your methods when it comes to, say, just improving acceleration? Are there any insights as to how you would use these methods to do such things?
Only acceleration?
Yeah, just focus on that. Are there certain components that you specifically look at and target? Because I know that, you know, say basketball, they don't sprint for very long stretches.
Yeah. So say that a basketball needs to be good over 2 to 5 steps. All right, let's say that, because everything is here. 2 to 5 steps, if you take the entire spectrum of these players, it means the first third or half of the spectrum. One thing that people need to really keep in mind is that when you accelerate all out, your maximum speed is reached within 2 or 1.5, your half of your maximum speed is reached between 1 and 2 seconds. So it means that even if the effort is 1 or 2 seconds, you already go very far into that velocity spectrum. So my opinion is that you should assess everything in these players, and you should focus on the left part of the spectrum, which is how much force do they put onto the ground, and how horizontally is that force oriented. Of course, you don't want to target a maximum effectiveness. That doesn't make sense, because they would jump horizontally and fall down. But if two players, you take the same vector and you orient that vector a bit more horizontal, and you look at the horizontal components, one reviewer of that Journal of Biomechanics method told us, guys, you don't need to do all that stuff to prove it's Newtonian mechanics. Why are you doing all these validation stuff, and the horizontal component of the force is driving the center of mass, and that's it? And we said, well, you know, in sports science, sometimes you need to do some stuff to convince people that. So I would work on how horizontally is that force oriented. So some players have very good force orientation, but not very good magnitude of force. So that's going to be, it's like a decision tree. Okay. So we will push them to maybe the gym to improve that level of force and try and maintain that orientation. And some players within the same team are exactly the opposite. They have not that much force output, but it's crazy well oriented. And you see these pictures of Allen Iverson, of these kind of players where you see their body are totally horizontally oriented for a V-cut movement or whatever. You know, they don't push really hard compared to maybe others, but they push so well in the good direction, in the direction they want to reach. And every player has a scenario.
Yep. When is the best time or the appropriate time to start looking at low velocity or force velocity curves for sprinters? You know, is that a 13-year-old? Is that 20 years old? When in the adolescent process? When do we start? People are asking, like, when do we start to apply this? When does it make sense?
Very good question. I tend to follow the advice by Stu McMillan, form first and load second. My answer would be, when they're young, have them run correctly, have them, you know the basics of good upright sprinting and acceleration steps, have them avoid false steps when they start everything, you know, into their pattern. And I would start when basically they start adding some strength into the system between 15 and 18, let's say, because between 15 and 18 you will start to have something that's more or less stable in boys, a bit earlier in girls. But you can measure that anytime, because remember, everything you need to assess the profile is them running from 0 to top speed. So there's been some publications on young people developing. But in terms of resisted sprints, it should be exactly the same philosophy. In my opinion, resisted sprints is just another specific strength exercise. So you should follow the exact same guidelines by people like Feigenbaum and all that, Rodri Lloyd, that you follow on strength. Do that on sprint specific strength. Okay, with the same progression, care. So to me, there's no reason not to do that after 15, 16. but they need to run correctly before that, because it's going to be modifiable later in their athletic life, but everything you don't get, technically speaking, at 16, 18, it's going to be tough afterwards to work on that, in my opinion, yes.
All right, we got in a ton of questions here, and unfortunately we are out of time. So I think that concludes this webinar.
Sorry, Peter, breaking in here. There's a lot of questions. I'm fielding the questions here to the guys. JB, do you have another 10 minutes to take a few more questions?
Sure. I'm locked down at home. What can I do?
Watching and I don't want to cut them off too short. So if you don't mind, let's continue for another 10 minutes.
Yeah, the
for
fresh
those who have
beer
to
is
leave,
waiting.
thank you very much, and we'll see you next time.
Awesome. Well, I got one here, Ola. Couple just probably simple questions for you, JB, but people that aren't used to using this kind of testing, what loads do you recommend from a methodology when you're doing the sprinting? And then what distance is the minimum that we should be testing? Let's say a football player.
Yeah, very important. So for the force velocity sprint test, you need them to run from 0 to their top speed. So basically, for most people around the world, it's something around 30 meters. But for example, some very high, tall, and heavy basketball players, it's going to be shorter. Some elite athletes like Bolt and all, it's going to be longer. So the testing is 0 to top speed, non-negotiable. So if you observe that top speed is reached earlier, then you can cut some distance. Okay. Now for the loads, it's very simple. We've observed that you have very, very clear results and very, very actionable relationships with 0% of body mass. So that's the free sprint. So sprint number 1 is the sprint you did just before. You use that as a point. So that's your Vmax and 0 kilo. And then a good practice we have is 25, 50, 70% of 75% of body mass. So you would say, okay, you said not body mass. We don't care. Here, it's just a way to have 3 different loads. Okay, because if you have 3 different points, that's going to make 4 points, and you're going to have the entire relationship. So if these 4 points are 25, 50, 75, or very sophisticatedly calculated points, you will end up at the end of the day on the same line. So don't go too much. So need to be okay and used to sprint with up to 75% of body mass. So again, if the athletes have never done that, don't do it. Don't do it until you spend 8 weeks, 16 sessions, ramping up to that. Now you're okay, we can test you. I think the big mistake that's done and the reliability of data is impacted is when you start something like from scratch, they never pulled nothing, and you go to, yes, of course, you're going to end up with wrong data. So progressively to 25, 50, 75% body mass. The points need to be widespread there.
One question here from Kyle that I think many coaches wonder about. How would you use the force velocity profile and load velocity profiling with a team consisting of 90 athletes? Ref American football.
You have to hire people. Now,
that's a short
yes, of course, it's a challenge. If you coach 2 tennis players, it's going to be easier. I have experience with hockey teams, football programs at the university in the US, and rugby teams here with 50 players. Basically, testing is done every 2 months, and that's some data analysis. But if you have some people able to code and to analyze data quickly, I mean, it's exactly the same question as maximum aerobic speed or any type of physical testing. If you want some variables, sometimes you have to spend some time testing. And if you have 90 players, that's going to be some testing time. So I cannot compress that. The alternative is don't do that and don't have the information. So yeah, of course, it's testing time. But okay, people spend hours and hours and hours processing GPS data. Okay, so it's just a matter of priority. Do you think it's a priority? Do you think you need to spend time on that? Can you get some brains trying to shorten the testing time? In the rugby club I work with now, when the player has the sprint finished, he comes back and he has everything displayed because they ask some data analysts to do some routines, and it's faster. So
JB, can you speak more, and you brought this up and emphasized it, but why you recommend velocity as the as kind of the what we're looking at over load when we're training sprinting? Like that's the thing we're thinking about specifically, like in a team setting, that we're not just worried about the load.
Yeah, so maybe 10 years ago, I said sometimes you have basketball players, you have football players, they never sprint more than 10, 15, 20 meters in the game, so forget high speed running. I did that. I'm totally in disagreement with myself for two reasons. Now, one is very well detailed by Ken Clark, and it's important. You can never reach the short contact time / high force production that you have at high speed with any gym exercise, any plyometrics, nothing. So there's no other way than maximum running speed, sprinting, to have your athletes pounding the ground hard within a short contact time. So if you want your football players, soccer players, rugby players to be able to run fast and to be very quick onto the ground, you need that high-speed stimulus. That's number one. And the second thing that you can never reach in another exercise than high-speed running is the hamstring, posterior chain, and very likely Achilles tendon and triceps muscles strain and velocity of movement. Because when you do isolated exercises of the posterior chain, you have tension, but you never have the range of motion, you never have the fast actions that you have in sprinting. So that's 2 points that, in my opinion, make high-speed sprinting important in team sport players, regardless of their actual need during the game. Because there's a lot of hamstring injuries in basketball. There's a lot of, you need that two components. And unfortunately, it's not negotiable. You cannot reach them in isolated exercises. There's been clear studies on that, like EMG activity of the hamstrings and all that stuff. Sprinting, top speed sprinting is totally another story.
One question here that I think you alluded to a little bit. Could you give an example? So when towards the end of the presentation, you showed same times, sprint times.
Yeah.
But could you give an example of workout used for an athlete shown previously, or the two athletes that you showed? And how you would approach them a little bit, kind of give an examples to give the viewers a little sense of that.
Yeah. So of course, sometimes the same split time is exactly the same profile. I took that example, but so if you have these two players that are really different, the idea that we are following now with that elite rugby club, so it's a 2-season study, is that they have basically 2 speed-oriented sessions during the week. One is basically common to all athletes, regardless of their profile. They do the basics, okay, for speed. And the other one is a session where we are going to orient very simply the stimulus to cover what's, in our opinion, the missing part of the profile between these two athletes. So we don't have absolute normative values right now. We just have comparisons within the group around the median of the group, who is much lower, much higher. Okay, it's a very straight, simple way of approaching things. But if you have a 50 players group in rugby or a 30 players group in rugby, this is what we do. So typically, the players with a low force / high speed profile, they're going to be they're going to have less maximum speed sessions or reps in their program, not 0, but less. And the button will be pushed on the other end of the spectrum. So they're going to do more high resistance work. And if we observe that this low horizontal force at the beginning is also explained by a low level of force output overall, they are going to do some gym work as well, because we want to improve their strength level overall. So strength plus orientation. And then what's very good is that we follow them every 2 months. So it means if we start that to modulate, I call that modulation of the training. If we start to individually modulate things and we see improvements, corrections, if we see something doesn't change or whatever, we can think again, because maybe something is wrong. You see what I mean? So this is very humbly what we are doing. It's been 2 seasons. Unfortunately, now it's been stopped. But, and again, the staff and the players, they will not come back to some one size fits all. We all do the same stuff, because they felt we were tackling something that was kind of missing.
Peter wants to stop now, but I want to throw in one more question. Going back to basketball.
Yeah.
Do you think a force velocity type profiling would be applicable to change of direction?
I don't know. Conceptually, I would say very likely, because change of direction is just accelerating and decelerating and reaccelerating in other direction. But there's one common feature, is that you need to be good at change of direction. You need to accelerate a lot in that new direction you're changing. So conceptually, it would make sense, but until we have clear measurements with good force velocity tests, reliable data, and good change of direction tests, and correlations between the two, then we can further discuss. But for now, not sure.
All right, Peter, that was a wrap.
Yeah, I wish we had more time, but